This is Captain Chaudhari in my series of videos on marine astronomical navigation. Today I want to do how to find out the transit time between the body rise and body set. For example, sunrise and sunset. Similarly, moonrise, moonset, or rising of star to setting of the star. We have also learned in my previous video I talked about the rate of change of meridian by different heavenly bodies. Like sun changes the meridian at the rate of 15 degrees per hour, moon changes at the rate of 14 degrees 19 plus V per hour, planet changes a meridian at the rate of 15 degrees plus V per hour, and Aries changes the rate at 15.041 degrees per hour. So suppose you are given a latitude and declination. Say latitude is 30 degrees north and declination of, say, moon, let us take as 28 degrees south. We want to find out the travel time from moonrise to moon set. So let us say this is the celestial sphere. In the plane of observer's rational horizon, this is west, east, north, south. Z latitude is 30 degrees north. So if we say we divide it in so many parts, 30 degrees north. And the declination of the moon is 28 degrees south. 10, 20, 28 would be something like this. So this is the apparent path of the moon. We can call it D dash D. The moon rises over here and sets over here. North celestial pole would be the same distance down from the north position. This is north celestial pole, and suppose the moon is rising here. This is the meridian passing through the moon at the time of moonrise. As you know, a meridian that passes through exact east point would be 90. You can see that this angle looks like less than 90 degrees. At the time of rising, the side ZX is 90 degrees. So we make the Napier diagram accordingly. Whatever is 90, you write down on top. The neighbors of ZX, without looking at the diagram, you should be able to say Z and X. Neighbor of Z, without looking at the diagram, you should say ZX and PZ, ZX and PX, and the remaining angle P. So this is what is the Napier diagram. In any astronomical calculation, whenever we have to find out duration, we have to attack the angle P. We must find out what is the angle P. So here what we are trying to find out is, as the moon travels here at the time of meridian passage, the moon's meridian would have traversed this angle. So we want to capture this angle. And if we do double of this angle, we will find out how much is the angle meridian crossed, or how much is the change of meridian from moonrise to moonset. So our basic aim right now is to find out angle P. What we know in this question is latitude, so therefore we know PZ, and we also know the declination, so we also know PX. So the relationship would be sine of 90 minus P is equal to tan 90 minus PZ, tan 90 minus PZ, tan 90 minus PX. But because one of the sides in the Napier is 90 degrees, we have this rule that if on the right hand side both are sides or both are angle, we introduce a negative sign. So there will be a negative sign on top. So I will write it here. It will become sine 90 minus P will become cos P, and tan 90 minus PZ, as you know, I have introduced a minus sign there on the right hand side. 1 upon tan PZ will be the first term and 1 of tan px is the second term. So this will be equal to -1 divided by tan 60, and you can see that px is 90 plus declination, so 90 plus 28, that is 118. Shift cos, I get 72.12. 72.12. If I multiply this by 2, I get the angle traversed till the moon set, so it becomes 144.24. In this question, what I have not given is the average value of V. So suppose the average value of V was 11 minutes. So the rate of change of meridian by the moon would be 14 degrees 19 plus 11. That means 14 degrees 30 minutes per hour. So if the rate of change of meridian by moon is 14 degrees 30 minutes per hour, how much time will moon take to cross or to traverse an angle of 144.24 degrees? So this will be divided by 14.5. In terms of hours, it is 9 hours 56 minutes or 56.4 minutes. So 9 hours 56 minutes and 53 seconds. So nearly 9 hours 56.4 minutes. This is the duration from moonrise to moonset. So this is how, when I know at what rate a body, heavenly body, is changing meridian, I can find out what is the duration from moonrise to moonset. Now we will try to find out the duration of daylight. That means what is the period from sunrise to sunset. But I will also want to tell you at this moment, like, how to find out the twilight. What is this twilight? Well, when the sun is below the observer's rational horizon by 18 degrees, we say that the astronomical twilight starts. And when the sun comes 12 degrees below the observer's rational horizon, we say that the nautical twilight has started. And when the center of the sun is 6 degrees below the observer's rational horizon, we say that civil twilight has started. And we say that as soon as the sunrise takes place, all the three twilights together abruptly stop. Similarly, at the time of sunset, from sunset till the sun center is 6 degrees below the observer's rational horizon, the civil twilight lasts, right? Which means that all the three twilights must start at the sunset. When the sun is 6 degrees below, civil twilight will end. When the sun center is 12 degrees below the observer's rational horizon, nautical, and when the sun center is 18 degrees below the observer's rational horizon, the astronomical twilight will stop, right? So morning, all the three twilights stop at the same time, and in the evening, all the three twilights start together. So this is what we have to understand. So on an observer's rational horizon diagram, suppose we take a case of latitude, some northerly latitude, and let us say the sun on the northerly declination 2, and let us extend this apparent daily path. Let us say the sun was here and this distance was 108 degrees. That is, the true zenith distance is 108 degrees. At that time, if we calculate the angle P, like this calculation will have to be done by cosine formula, right? And if we find out what is the angle P, we are able to find out how much time the sun will take from here till meridian passage. And later on, when the sunrise takes place, we again calculate this PZX1 triangle and we find out what is the angle P1. Right? So we are going to solve two spherical triangles, PZX and PZX1. The difference of the angle that is subtended at pole, that is P difference P1, will help us to give you will help us to give us the duration of twilight. This is the duration of twilight or duration of astronomical twilight. So let us say that the latitude is 30 degrees north and let's say declination is 12 degrees north. Right? So while the sun is here, we say that px is 90 minus 12, so that is 78 degrees, and pz is 90 minus latitude, so 60 degrees, and the side zx is 108 degrees. So can we find out angle p? So cosine formula means, suppose we say the side opposite to p is small p, side opposite to z is small z, and side opposite to x is small x. We say that in case I want to find out angle p, I will write down the formula first for side p. So cos of small p is equal to cos z cos x plus sine z sine x into cosine of opposite angle p. So therefore cos of opposite angle p should be equal to cos of small p minus cos z cos x divided by sine z sine x. So that is cos of 108 degrees minus cos 60 cos 78 divided by sine 60 sine 78 degrees. So that is cos 108 degrees gives me 119.17, 119.17 degrees, or we can take it as 18 degrees. This is the angle P. Now in case I want to find out angle P1, probably I can use the same formula, but instead of cos 108 I will be writing cos 90. It can also be done by Napier, but I'm just saying instead of 108, if I write 90, I can do this triangle, and cos of 90, as you know, is 0. So effectively what we get is cos of angle P is equal to cos 0 minus this upon this. So this can be written as minus 1 divided by tan 60 tan 78 degrees. So minus 1 divided by tan 60 degrees into tan cos gives me 97.05, 97.05 degrees. So if we say that we know only this angle, that is from sunrise to meridian passage. If you look at this triangle, we have found this angle as 97.05, and 97.05 multiplied by 2 will give me the angle traced till the sunset. That means the total angle, that is 194.098 degrees. If I divide this by 15, I get 12.939. In terms of hours and minutes, it will be 12 hours 56 minutes and 24 seconds. So this is the duration of twilight when the latitude is 30 degrees north and sun's declination is 12 degrees north. But here in this question, basically we are trying to find out what is the duration of twilight, that is astronomical twilight. So what we'll have to do is we'll have to subtract 97.05 degrees from 119.18 degrees. So 119.18 minus 97.05 equals divided by 15. So many hours is the duration of twilight. Right? If I multiply this by 60, I get, in terms of minutes, it is 88.5 minutes. 88.5 minutes is the duration of twilight. That is 1 hour 28.5 minutes is the duration of twilight. If I had to find out the duration of nautical twilight, I would have done the similar calculation, but I would have used this side initially as 102 degrees and then as 90 degrees. I would have got duration of nautical twilight. Now, just to get a brief idea of what is this civil twilight, nautical twilight, and astronomical twilight. In a layman's way, like civil twilight is the one where you identify the people, you recognize the features, like it is as good as the broad daylight, but sun is below the horizon. That is civil twilight. Astronomical twilight, on the other hand, is a twilight where without any fail you are able to look at the stars. It is dark enough. You can see the stars, but unfortunately, you probably cannot see the horizon clearly. It's not clear enough for a sight to be taken. And nautical twilight is a twilight in between, whereby you may not be able to recognize the people at distance, but you are able to look at the star as well as the horizon at the same time. So that is the suitable time, when you take the sight. So that means this is a suitable time for taking the star sight. Like when the center of the sun is 6 degrees to 12 degrees below observer's rational horizon.